Hi everyone, this is Mr. Bowman and welcome back to the second day of inference for slope. On the first day, if you recall, what we had was a random sample of 22 different pairs of duration of eruption and the interval between eruptions for Old Faithful from a sample of from 2005. And what we did from that is we estimated the slope of a population line of best fit by coming up with a confidence interval for it. Today what we're going to do is we're going to talk about doing hypothesis tests for the slope. And typically what we do with that is we say that there's some useful relationship between the two variables. Another way of saying that is that the null hypothesis is that the slope of the population line of best fit is 0, and the alternative is it's either less than 0, greater than 0, or just not equal to 0. So let's take a look at this. In this case, the null and the alternative hypotheses for our Old Faithful data would be the following. It would be the null hypothesis is the slope of the population line of best fit for predicting interval from duration is 0. Remember, this is a statement about the population line of best fit slope. So it refers to all the data, but it's going to be based on our sample of size 20. Another way of saying that is there's no linear relationship. The alternative in this case is that the slope of the population line of best fit for predicting interval from duration is not 0. We're not suggesting it's greater than 0 or less than 0. We're just saying not 0. So as you know, we use a t-statistic for slopes. So we are going to calculate the test statistic the way we always do. Statistic minus hypothesized value over the standard deviation of the statistic, which then becomes this right here that I highlighted in yellow. And when we have a null hypothesis where we're saying that the slope of the population line of best fit is 0, we call this a t-ratio. And it's simply the sample slope divided by the standard error of the sample slope. Very often we're given this information in the form of computer output. So as you can see here, our data in the form or computer output based on our data is right here. The slope of the sample line of best fit is 14.19 and the y-intercept 31.196, and this would be our prediction equation. The predicted interval is about 14.19 times the duration plus the y-intercept of 31.19655. So in this particular problem, it says, using the Minitab output above, compute the t-statistic and find the p-value. Draw an appropriate conclusion. Okay, well, our hypothesized value for the population slope was 0, so we're going to calculate the t-statistic by taking the sample slope divided by the standard error of the sample slope. So essentially, we're going to take this number and divide by that number, and that gives us our t-ratio, which should go in the green box, which is just blank for now. So as you can see, 14.19 minus 0 over 1.35 gives us a t-value of 10.47, which essentially tells us that our sample slope, if the null hypothesis is true, our sample slope is about 10.5 standard deviations above what we hypothesized. Okay? Under any circumstances, that would result in a very small p-value. Recall that the degrees of freedom for bivariate or two-variable quantitative data is n minus 2, and this p-value is 4.35 times 10 to the negative 9. And again, that would go in the box that I'm drawing right now. If it were there, I left it off just so we can talk about how to calculate it. So our conclusion would be to reject the null hypothesis and say there is evidence that the slope of the population line of best fit for predicting interval from duration is not 0, i.e. there is a linear relationship between the explanatory and the response variable for the population. The next thing I would like to do is show you how to do this on the calculator. So if you want to pause the video a moment and enter this data, the duration will go in list 1 and the interval will be in list 2. We're going to predict the interval based on the duration. Alright, so this is a bigger data set than you would be given on the AP exam because they don't want you to make a mistake entering the data. But as you're entering the data, make sure you take your time doing that and pause when you get to your last entry in your last list and put the cursor on that and make sure that you have the right number of pieces of data in both your lists. The next thing we're going to do is we are going to perform a linear regression t-test. We already looked at scatter plots and residual plots yesterday, so we already know we meet the conditions. We're not going to do that again. But if you go to Stat and go over to Tests and go to Linear Regression t-test, all right, X list is in list 1, Y list is in list 2. We're going to count each value once. Our alternative hypothesis, you'll see that beta and rho. Basically, beta is the slope of the population line of best fit, and rho is the correlation for the population relationship between the two variables. If the slope is 0, then rho is 0. But you don't have to be concerned about rho. Just think about it in terms of the population slope. If you want to store the regression equation in Y1, then you can do that by putting the cursor in a regression equation and hitting alpha trace and then enter, and then let's go ahead and calculate. Alright, so we calculate this, we get our test statistic t, you see it there that we got a few minutes ago, our p-value, which is pretty much the same as we got before. Any differences are rounding. Degrees of freedom is 18. You will notice that in doing the linear regression t-test on the calculator, it gives you both the sample slope and the sample y-intercept. It gives you the standard deviation of the residuals, aka the error in the predictions, and then it also gives you r and r squared. So if you hadn't looked at the least squares regression equation with the scatter plot, you could turn the scatter plot on now and you could look at the residual plot if you wanted to and check the conditions and so on and so forth. But otherwise, that's how you do a linear regression t-test on your calculator. So what I would like you to do right now is I would like you to pause the video and take a look at the next question. And the next question is from an old AP exam. So read that and see if you can do parts A, B, and C, and then unpause the video and I will go over the answers to that. Alright, if you read the stem of the problem or look at the scatter plot, you will see that the data consists of 7 different speeds in miles per hour and 7 different beats per minute. Based on the computer output, we can look at what the explanatory variable is, and that is speed, so the response variable is pulse. You can see that from the scatter plot as well. And our prediction equation for the sample data is predicted pulse is equal to 16.2809 times the speed plus 63.457. And as far as interpretations of the slope and the y-intercept, we would interpret the slope as speed increases by 1, the pulse is predicted to increase by 16 beats per minute. And if the speed is 0, it's predicting a resting heart rate of 63.457 beats per minute. And then finally, the last part, if you're going to do a 98% confidence interval, use the inverse t function or look up the t critical value on the t-table. And use 5 degrees of freedom, and you would get a critical value of 3.36. So to calculate the margin of error, you would take the critical value times the standard error. The standard error is 0.8192, and you can get that from the computer output. You see I have it circled there. And that's all you have to do for that problem. Just to make sure that everybody's got the idea, there is one more practice problem here. It is the 2001 question number 6 part of that. So if you'd like to pause the video for a moment, read through that question, see if you can answer the questions. I'll go over it in just a moment. So you'll notice in this problem that it's a relationship between GPA and credit hours that a student is carrying. What you'll also notice is that in the two tables, they split the data out between people who successfully completed the PhD program and people who did not. They also did that for the computer output. And then in the question itself, it says, we would like to determine if there's evidence of a linear relationship between GPA and average number of credit hours per semester, underlined, for the students who successfully completed the PhD program. So make sure you read that carefully. So the first part asks you to write the regression equation for the sample. That is simply reading it off the computer output for those who completed the PhD program. That's the first set of computer output here. Here's the slope, here's the y-intercept, and GPA is the explanatory variable. In the second part, do your estimates of the slope and the intercept parameter have meaningful interpretations in context of this question? If so, provide interpretations. As GPA increases by 1 hour, credit hour is predicted to decrease by 2.755. And the y-intercept would say somebody with a 0 GPA, so it makes no sense in this particular context. All right, in the next part of this question, it says check the necessary conditions, construct and interpret a 98% confidence interval for the true population slope in context. So remember, there are 5 conditions that you need to check. Remember that mnemonic, liner, linear, independent, normality of the residuals, equal variance of the residuals, and random. So not necessarily in order. Here they are. Random sample is stated. I put this data in my calculator, and the data plotted appears linear. It's supported by the scatter plot, the values of R, R squared, and S, and the residual plot. You can see small printouts of those below. That's all stuff you'd have to check on your calculator. The 13 students is likely less than 10% of students that completed the PhD program over the last year, so it seems reasonable we meet the independence condition. Here's a normal probability plot of the residuals. It suggests that credit hours are normally distributed at each of the values of GPA. And looking again at the residual plot, it appears that the variance in the credit hours are equal, so for each value of X. So it looks like we met the 5 conditions. Here's our confidence interval from the calculator. You can find the critical value for that confidence interval by using inverse T of 0.99 and 11 degrees of freedom. And here's the necessary work for that confidence interval. And then finally, we are 98% confident that beta, the population slope of line of best fit for predicting GPA from credit hours, lies in the interval from negative 4.205 to negative 1.306. The next part of this question asks you to test the appropriate hypothesis at the 2% level of significance to determine if there's evidence of a linear association between the two variables. So our null hypothesis is that there is no linear relationship between credit hours and GPA of students who successfully completed the PhD program. And the alternative is there is a linear relationship between credit hours and GPA of students who successfully completed the PhD program. So our T ratio, you can calculate, shown by the formula there. It's taking the sample slope, dividing by the standard error of the slope, or you can read that just off the computer output. You can also find the p-value. Don't forget, it's a two-sided alternative, so find the area to the left of negative 5.90 and then double it. Or you could read the p-value off the computer output, which says that it's 0 to 3 decimal places, which is consistent with what you see here. In either case, we would reject the null hypothesis, and there is evidence that beta is not equal to 0, i.e., there is a useful linear relationship between the two variables. And then the last question says, explain how the results from part C and D agree with each other. Well, if you recall, in part C, we got a confidence interval that did not contain 0, which is strong evidence that the population slope is not 0. And in our hypothesis test, we rejected the hypothesis that beta is 0. So we have strong evidence there that beta is not equal to 0 as well.